Hey everyone, this is going to be the first quantum mechanics problem that I'm doing on the channel, and it's going to be the classic particle in a box problem. Particle in a box. Or particle in an infinite square well. Infinite square well. The setup of the problem is this. There's a box. The edges of the box have an infinite potential. So here's the space axis. We're gonna keep it one-dimensional in space. And here's the potential axis. And the sides of the box have infinite potential, which means that the particle is confined to the box, cannot quantum tunnel through the sides, can't get out of the box. It's somewhere in the box. And the box is a length L. Okay, let's define the origin of the space coordinate to be at the left side of the box, and the right side is at a distance away, L. So the total width of the box is L. And then to be explicit about the potential as a function of x is equal to 0 between x and L. Between 0 and L, and it's infinite elsewhere. So the potential is 0 in the box, and it's infinite at the sides of the box and outside the box, which means the particle is in the box 100%. So let's just straight up start. We gotta write down the time independent Schrodinger equation. And since we're in one dimension, I'm gonna skip the partials and just go to full derivative. Vx psi is equal to E psi. Here's the time independent Schrodinger equation, but remember, we know for a fact that the particle is in the box, which means that the wave function is 0 outside of the box, which means that this term in the equation is 0 where the particle is, which means that the Schrodinger equation simplifies nicely. D squared psi dx squared is equal to energy times psi. This is a second order differential equation. You could do a change of variables to get rid of this mess out front, but this is a classic differential equation, and the solutions are sinusoidal, either sine or cosine in general, a combination of sines and cosines. So you can feel free to look it up. I'm not going to solve that here, but they are a combination of sine plus cosine. What's the argument of the sine and cosine? All right, so to figure out what's going to go in the sine, let's take a look at the box. So we know that the potential at 0 and L is infinity, which means that the particle is not at the very edge of the box. So the wave function must go to 0 at the edge of the box. So whatever we plug into sine or cosine at 0 and L, it better make the whole thing 0. Sine must be 0 at L, and it also must be 0 at 0. So if we have an x, and we plug in 0, sine of 0 is 0, so that's a good start. But cosine of 0 is 1. That's not going to work. So we got to throw out this term. And now we know that the wave function is just a sine term. So again, sine of 0 is 0, but then we need to make it 0 also at L. How are we going to do that? It's got to be, we're going to make it L in the denominator. So if we plug 0 over L, that's still 0. It makes psi 0. If we plug L in the numerator divided by L, that's 1. But if we multiply it by pi, 1 pi, sine of pi is 0. So that fixes it. 0 pi, sine of 0 pi is sine of 0, makes psi 0. And sine of 1 pi is also 0, it makes psi 0. Sine of 2 pi is also 0, 3 pi, any integer number of pi actually. So n pi x over L, if we plug in L, then at the boundary condition, psi is still good. So the argument of the sine function is n pi x over L. Any integer number of pi's will do the trick. So we said that psi of x, the wave function, the function of x, is equal to some coefficient a times sine, which is the amplitude, n pi, n x pi, whatever, over L. And this n is going to turn out to be the quantum number, and each one, so psi of n, each one is going to be like the state of the particle. So there's a ground state, there's a first excited state, second excited state, and those are represented by the quantum number n. And physically, they're going to be how wavy or wiggly the wave function is in space. So, and how many nodes it has. So you think normally, okay, ground state, this should be n equals 0, but remember, if we plug in n equals 0, it makes the whole thing 0, and then there's no particle, so it can't be the ground state. The ground state is n equals 1. N equals 1 is the ground state, and that's sine of pi x over 2. N equals 2 is the first excited state. First excited state is n equals 2, and so on. They have, it crosses the number of times it crosses the x-axis is equal to n minus 1. But anyway, here we are so far. Ground state is n equals 1. We still need to figure out what a is. The problem asks us to the problem asks us to first find the corresponding energy levels, and then to normalize the wave function, and then to find the probability that the particle is between 0 and L over 3. So what's the probability that the particle is in the leftmost third of the box? But first we got to solve for E. How are we going to solve for E? Plug it back into the Schrodinger equation. D squared psi dx squared is equal to, okay, let's say the first derivative of this is a cosine n pi x over L times n pi over L. And the second derivative is minus a sine n pi x over L times another n pi over L. And that's equal to E times psi, which is E times A sine n pi x over L. What's the same on both sides? The same on both sides is this A sine n pi x over L. So we're left with E is equal to, this minus h bar squared over 2m is multiplied by this. So we're left with minus h bar squared over 2m times n squared pi squared over L squared equals, there's a minus sign here, and there's a minus sign here, they cancel, equals E. So each energy level, E sub n, is equal to n squared pi squared h bar squared over 2m L squared. So the ground state energy, E1, equals pi squared h bar squared over 2m L squared. You can look up the value for h bar squared, give whatever mass you want to the particle and whatever length of the box you want it to be, plug it in and you'll get a number. I'm not going to do that here, but that's the energy. Those are the energies. Okay, part B. Part B is going to be to normalize the wave function. Remember, size of n of x equals A sine n pi x over L. What is A? We gotta find A such that when we square the wave function, we get 1. Because the square of the wave function physically represents a probability density. So if we square it and integrate over all space where we know the particle is, which just turns out to be the width of the box, we better get a probability of 1, meaning the particle is definitely in the box. So the integral from 0 to L of psi squared dx is equal to A squared. I'm going to pull it out of the integral because it's a constant. Sine squared n pi x over L dx. Now, there is a trig identity that says sine squared of theta is equal to 1 minus cosine 2 theta all over 2. It's a real trig identity, feel free to look it up. I'm going to pull the 1/2 out of the integral. I'm going to pull a minus, no, I can't do that actually. Not 1/2, it's yeah, I pulled the 2 out. Right, so we're left with 1 minus cosine 2n pi x over L dx, of course. This term is just going to be x, right? If you integrate 1 dx, just get x. From 0 to L is L minus 0 is L. Minus, let's see, the integral of cosine theta is sine theta, but then reverse chain rule, we're gonna have to divide by the coefficient in front of the argument, so it'll be sine theta sine 2 n pi x over L times L over 2 n pi evaluated from 0 to L. Let's see, if we plug L in here, we're gonna get 2n pi. Sine of any integer multiple of 2 pi is always 0. And if we plug 0 in for here, sine of 0 is 0. So this is 0 minus 0 equals 0, which means that this L term only survives, and we're going to get 1 is equal to a squared over 2 times L. Multiply both sides by 2, divide both sides by L, square root. A is equal to square root of 2 over L. And that's how we normalize the wave function. So now let's go back. Sin sub n of x is actually equal to 2 over L. Sine n pi x over L. Okay, so there's the wave function normalized. And then the last thing we have to do is find the probability of the particle being in the leftmost third of the box, so between x equals 0 and x equals L over 3. And the way we do that is we integrate again from 0 to L over 3. We integrate the wave function squared times space. Remember, I told you that squaring the wave function squared is a probability density. And the density is always divided by space. So if you multiply by space and then integrate over the region that you want to solve for, you get the probability. So psi squared dx is going to be equal to so obviously the 2 over L square root squared is 2 over L. I'm going to pull it outside the integral. This is sine squared n pi x over L dx from 0 to L over 3. I'm going to pull the same trig identity trick. So it'll be, I'm going to pull out the 2 on the denominator. It'll be 2 over 2. This is now 1 over L. 0 to L over 3. 1 minus cosine 2n pi x over L dx. Again, this 1 dx integrated is just x. L over 3 minus 0 is L over 3. So this is 1 over L times L over 3 minus cosine. Integral of cosine is sine times this divided by the coefficient in front of the argument. 2n pi x over L times L over 2n pi evaluated from 0 to L over 3. And that's equal to the probability. Let's see, if we plug L over 3 in for x, the L's will cancel. All right, hold on. First off, if we plug 0 in for x, it's going to be 0. If we plug L over 3 in for x, we're going to get 2/3 pi times n. I also forgot to mention, I forgot to mention that we have to pick a state. We got to pick a state. So let's say it's the ground state. So that means that the n is 1 everywhere. The n is 1 everywhere. So we're interested in the ground state. What's the probability of finding the particle in the ground state in the leftmost third of the box? If we plug L over 3 in, we get 2 pi over 3 sine of 2 pi over 3 is equal to root 3 over 2. Remember that from the unit circle, it's root 3 over 2 times L over 2 pi times 1 over L. All right, L over 3 minus that. So the probability is equal to 1 over L times L over 3 minus root 3 over 2 times L over 2 pi. This L will cancel with this, and this probability is equal to 1/3 minus root 3 over 4 pi. And if you plug this in your calculator, it's approximately equal to 0.1801. So the probability is 18.01% that you find the ground state, a particle, if it's in the ground state, in the leftmost third of the box. This is kind of a complicated. Quantum mechanics is complicated. Even the simplest problem, there's a lot going on, a lot of things to remember. But this is just kind of the simplest possible problem that you could do in quantum mechanics. So I thought it would be a good introduction video on my channel, but it's fun to do. So thanks for watching.